This is Chapter 5, Applying Newton's Laws. Now, this chapter is really just an extension of Chapter 4, and we're going to be using Newton's three laws as well as forces to look at objects in more detail than in the previous couple of chapters. So in addition to Newton's first and second laws, we're also going to look at friction and fluid resistance, or air resistance if you will, and talk very briefly about circular motion. So as I said earlier, we're going to extend the problem solving skills that we began to develop in Chapter 4, and we're going to start by talking about equilibrium, which is a case where the acceleration is equal to 0, which also means a constant velocity. Then we're going to start to talk about objects that are not in equilibrium. What that means is that they are accelerating, and look at force and motion. As I said earlier, we're going to look at the frictional force that acts when a body slides over an object, and the two types of frictional force. And last, we're going to look at the forces that are on a body in circular motion at constant speed. You might also see the words uniform circular motion, meaning constant speed. You've seen this problem-solving strategy several times, so I'm not going to spend too much time on it. But you want to first identify the parameters, set the problem up, execute it, and evaluate it, which is also an IC acronym. Coming from NASA, I have to talk about acronyms a lot. But really, what I want you to take away from this is you want to draw a simple sketch on what's going on. Very important. More importantly would be drawing the free body diagram, and then ask yourself what is interacting or touching in this problem, because you'll be definitely solving for those quantities. Choose your set of coordinate axes, and you want to choose them such that it makes your life easy. And when we talk about ramps, you'll see that today. Break everything up into components based on this coordinate axes, typically x and y. So we do that right here. And then in the case of solving forces, we typically would say, what are the sum of forces in the x direction, what are the sum of forces in the y direction, solve those two components separately, execute the problem, and lastly evaluate it. Does it make sense? Did you calculate a force of 10 quadrillion newtons? If you do this enough, then it tends to become ingrained and more natural as you're solving problems in this class, and that also makes solving the homeworks, the lecture problems, and the exams a lot easier. So I highly recommend that you work a lot of the examples that are in the book in this chapter. So let me dive right into it and talk about what happens if a gymnast is hanging from a rope on the ceiling. The book already has drawn a nice little stick figure for me. As I've said, my wife is the artist, I am not, so I'm shamelessly using their drawing. And it says a gymnast hangs at the end from a massless rope. The gymnast is just stationary, so the acceleration is equal to 0 meters per second. The free body diagram for the gymnast is going to have the weight of the gymnast pointing downwards, and then the tension on the rope pointing upwards. The free body diagram for the rope is going to have some tension due to the gymnast, and then it's going to have some tension due to its interaction with the ceiling. The ceiling would have a similar force downward, making an action-reaction pair. And you can see we do have one action-reaction pair right here, which is the tension of the gymnast, equal magnitude, opposite directions. And if we knew that the mass of the gymnast, as in the book, was equal to 50 kilograms, then we could say that the weight is equal to mass times gravity is equal to 490 newtons, where I've gone ahead and I've used gravity to be 9.8 meters per second squared. And we do the sum of forces in the y direction is equal to 0, because it's not accelerating. That's going to be the tension of the due to the gymnast upwards, and the weight in the downwards direction. So we can say that the tension due to the gymnast is equal to the weight, which is equal to 490 newtons. We can do the same thing over here and find out that the tension that is applied to the ceiling is also 490 meters. We can take this a little bit further by saying, well, what if the rope has mass? That makes it a little bit more difficult. Well, the free body diagram for the gymnast remains the same. We have the weight downwards and then the tension of the rope on the gymnast. Now if we consider the free body diagram for the rope, it's going to have the tension of the gymnast on there. This is G on R. And it's going to have some tension due to the ceiling. And now it's going to have another force downwards that's going to be the weight of the rope. And we can look at this as a composite body, where if I look at the free body diagram for the rope and the gymnast, then downwards I'm going to have the weight of the gymnast plus the weight of the rope, and upwards I'm going to have the tension of the ceiling. And again, obviously things aren't moving in the y direction, so the sum of forces in the y direction must be equal to 0. And here we have the tension on the ceiling upwards, and downwards we have the weight of the gymnast plus the weight of the rope. Make that a quantity. And if we know that the weight of the rope is, say, 120 newtons, then now we can say the tension on the ceiling is going to be equal to the weight of the gymnast plus the weight of the rope. We calculated the weight of the gymnast earlier to be 490 newtons. So the sum of those two is simply going to be 610 newtons. We can do this in 2 dimensions if we consider example 5.3, where we have a car engine hanging from several chains. First thing we want to do is draw the free body diagram for the engine right here. Now the engine is going to have its weight going downwards. It's going to be supported by T1 in the upwards direction. And we could do the sum of forces in the y direction for the engine, say that it's not accelerating, and come up with the tension in rope 1 is equal to the weight of the engine. Now if we consider the free body diagram for the O-ring right here, it's going to first have the tension 1 in the string in the downwards direction. It's going to have some tension in the string over here, tension 2. I'll also note real quick that here we have a T1. The T1s is an action-reaction pair, so the tension in T1 from this engine free body diagram is equal to the tension 1 on that free body diagram. And lastly, we have T3, which kind of comes off at an angle right here. If we do similar angles, this must be 60 degrees as well. So I can write 60 degrees right here. And we have T3. Now what we want to do is we want to examine this in both the x direction and the y direction. So the first thing we need to do is we need to break T3 up into T3 in the x direction and T3 in the y direction. All right, we're getting kind of familiar with breaking these two guys up. We can use trigonometry to say T3 in the x direction is going to be the magnitude of T3 multiplied by cosine of 60, and similarly T3 in the y direction is going to be T3 sine of 60. So now we can say, alright, what are all the forces in the y direction here? Well, we have negative T1 downwards, and in the positive direction we have T3y, and we can say the engine is not accelerating, so we can say these two guys are equal to mass times acceleration. Acceleration is 0. So T1 is equal to T3y. We can calculate T1 using the weight, again action-reaction pair, and the sum of forces in the x direction is going to be also equal to mass times acceleration. Acceleration is equal to 0. We're going to have negative T2 plus T3x, and we can say T2 must therefore be equal to T3x, and we can use essentially T1 to solve for T3y, and then use the trigonometry up here to solve for T3, actually to solve for T3 in the y direction, and then we can use that in the x direction to solve for what the tension in the string should be. Now looking at a car on a ramp, it's a little bit more interesting. We can say if you have a car on the ramp that's being actually held upwards, so the car rests, so acceleration is equal to 0. It's being pulled upwards with some tension force at some angle, and the car's weight always acts in the downwards direction. However, the normal force, I said, is the perpendicular force. That's going to be the force that is normal to the surface of the ramp. So the normal force is always going to be perpendicular to the surface. So it's not straight up and down as in the previous couple of examples. And what we want to do here is it might make it more simpler if rather than choosing the XY axis to be up down, but maybe choose our XY axis to be tilted at that angle. So this would be my x-axis, this would be my y-axis. Now I have my tension force and my normal force along that axis, and all I really need to do then is to break my weight up into the components that are along that axis. So here I would have my weight in the y direction, and here I would have my weight in the x direction, where that's some angle. Oops, that's also equal to that angle right there. Now, the reason why we might do something like that is simply because we only have to break one object into components rather than having to break that one up and that one up. It just makes our life a little bit easier. So now we would say, what are the sum of the forces in the, let's just say, x direction. The car is not moving, it's not accelerating, so it's equal to mass times acceleration is equal to 0. So in the positive x direction we have the tension, and then in the negative direction we have the weight in the x direction. Similarly, in the y direction we have no acceleration, and in this direction what we have is the normal force minus the weight in the y direction. We can calculate those. The weight in the x direction is going to be W times sine of the angle. Similarly, in the y direction it's going to be W cosine the angle between them. And if we're given the angle and we're given the weight, then we can solve for these two parameters right here. And I'll leave those as an exercise left to the student. If we consider bodies that are connected by a cable and a pulley, and very typically what we do is we assume that the pulley is totally frictionless, totally weightless, and the same with the rope that connects them. It just makes our life a little bit easier. If we draw the free body diagram, say for the cart, we're going to have some tension in the system, and we're going to have our weight downward as well as our normal force. And for the bucket, we're going to have the tension upwards and then the weight in the downwards direction. The tension is the action-reaction pair, so it's going to be the same. So if I look at my system for the bucket only, then downwards I have the weight, upwards I have the tension. I can say the tension is equal to the weight, which is going to be its mass times gravity. And if I can then use this tension, apply that in the cart's reference frame where I shift my XY axis perhaps, I can solve for the weight of the cart, say if these guys are being balanced. Better make that a 2 and a 1.